lastly to look at image processing issues. So image processing, basically there are two approaches one uses for image processing. One is called spatial domain processing, and we have the frequency domain processing. Okay. Now, before going into details of either of these, first I'd like to just give you a flavor of what each of these consists of. So spatial domain processing basically deals with neighborhood properties of the pixels. So if I have an image, so image is basically a matrix of intensities. Okay, if I take one particular pixel here, say pixel P with some coordinates x and y, then basically my image in the spatial domain is represented by this function here for all different values of x and y belonging to the image. Now the processing basically takes this image and applies a function or a filter to it to yield a different image. So if the processed image or pre-processed image is x and y both gxy, then it is some function of the original image fxy processed by a transform or a filter, you can call in general, this being our input image and this is the output image. This function h basically depends on the properties of the neighboring pixels, properties of P as well as the neighboring pixels. So typically what is done is that you have now one pixel of interest for now, and we have our image which is other neighboring pixels around it. So supposing I take a 3 by 3 neighborhood of this, then I basically have pixels left, right, top, bottom of it, and I have 8 neighboring pixels for the pixel of interest P. Okay, and this, if I assign it some weightages, so if I give this weightage W1, W2, W3, etc., etc., I have W4, W7, W8, W9. Okay, so I have assigned some weights to each of these cells. This I will call a template. Of course, other values are also there. I hope it's clear. Okay, these are basically weights W1, W2, W3, W4, W5, W6, and so on and so forth. So one of the pre-processing steps in general, we can show this as that our transformed image or processed image essentially is obtained by summing over all the neighborhood pixels of interest. Okay, so if I say sum wjk times the intensity at x plus j, y plus k. Okay, this is to be summed over all the j's, let's say in this particular case going from -1, 0, 1, and k going from -1, 0, 1. Okay, if I spell it out, basically this means that I am saying weight -1, -1, then I have to take the intensity x minus 1, y minus 1, right. Then I will take the next summation, next term, which will be minus 1, let us say, and 0, which will have to be multiplied by x minus 1 y. So likewise I can go plus 1 x minus 1 y plus 1, okay, and so on and so forth. So I will have 9 terms like this, where what I have shown here is this w1, for example, is w minus 1 minus 1, because it is corresponding to x minus 1 with relation to the pixel that we are looking at. So the idea is that you look at this particular mask or template and you take it from each, take it on each of the pixels of the image, starting from, let us say, upper left to the bottom right. Sequentially you place this mask, and placing the mask has the meaning of that you multiply the weights to the intensity and then find out the sum, and that is going to be the new value that you should assign to the value to the pixel p. Okay, the way you will do this is that you will go ahead and perform this operation throughout the whole image, and then after that you will replace all the new values. So the values will not be replaced as soon as they are calculated, but they will be replaced only when the entire image has been gone over by the template. So this one, for example, is going to be simply w1 times fx minus 1 y minus 1 plus w2 times fx minus 1 y plus w2 times w3 times minus 1 y plus 1. W4 I am writing in the same fashion as the x y minus 1 plus w5 f x y plus w6 f x y plus 1 plus w7 f x plus 1 y minus 1 plus w8 f x plus 1 y plus w9 f x plus 1 y plus 1. Okay, this is the meaning of a template. Okay, this is also called a filter. So depending on what weights are assigned, these filters have different effect on the image, and we will see some of these filters as we go along. Now one special case is worth mentioning. Special case is when the window that I am looking at, the template that I am looking at, is also 1 by 1. So 1 by 1 template, which means that for the image I am looking at the intensity of this particular pixel, and I am going to, it does not depend on any neighboring pixels, it only depends on this particular intensity value. So I can write this as some transformation of whatever this intensity R is gets transformed into a different intensity, which I am calling S. Okay, so this is called image intensity transformation. Transformation or mapping. Okay, this is a special case. Let us see, supposing what I am talking about is you have some kind of relationship between the input intensities. So I am plotting R here and S here. The value of S depends in some fashion to the input intensity, right. So this is, let us say, dark area, this is the light area. Here again I have dark and light. So the value of the intensity is 0 here, let us say, and 255 corresponding to the fully bright. So what is happening is, supposing now I look at, if I had a straight line here, then this straight line would correspond to no change in the image at all, right, because whatever the intensity corresponding to that, I will get the same value for the output image. So I would have done nothing at all. But if it is deviating from the straight line, then it is going to transform the image in some fashion, and this can be used for increasing the contrast or decreasing the contrast of the image. Okay, so we will look at this also. This is also part of the spatial space-based techniques. Now let us apply one of these masks as example. So this is example of spatial domain processing. Okay, let me take a mask, define a mask first or template. Okay, let's say I have put -1, -1, -1, -1, 8, -1, -1, -1, -1. Supposing this is my template, and then I take my image or part of the image, okay. So let me put some values, say this is 12, intensity 10, 11, 10, 12, let's say this is 11, 11, 10, 25, 11, okay, 10, 11, 10, 12, 10. I'm just, this is typically what the image will be in the computer, right? This is, so a set of intensities which are there in different pixel locations. So now if I fit this mask on the 3 by 3 area here, okay, so what I'll be doing is essentially multiplying this, the middle pixel intensity by 8, so I will have 88, and from that I'll have to subtract out all these things. So 12 minus 10 minus 11 minus 11 minus 10 minus 10 minus 11 minus 10. So whatever that comes out to be, maybe one of you can calculate and we can find out what this is. Now if I move this mask further, I will translate it to the next set of 3 by 3 matrix here. This should come out to be pretty close to 0, -1, okay, all right. Now you look at this area. Now I'm going to make it a little darker here. This is where I have placed the template, and I'm going to now apply the mask to this. So the next value for this particular cell I'm getting is 80 minus 10 minus 11 minus 10 minus 11 minus 25 minus 11 minus 10 minus 12. So this will turn out to be some value, maybe around -20 or something, -20. Okay. Then when I shift it further, so this is the area now I'm looking at, and so I will have 25 in the center here, which gets multiplied by 8. So I have 200 minus 11 minus 10 minus 12 minus 10 minus 11 minus 10 minus 12 minus 10, and this will turn out to be more than 100. Okay. So what I am trying to say is that depending on the mask, so this is the mask that we chosen, in which the weightage is very high in the center. Okay. Now that has a tendency to highlight anything that differs from the background. So if a single pixel is has much different intensity, then this mask will highlight that, because if the intensity was pretty much uniform, then you will come out to be close to 0, within some band of 0 you will come out. But if the intensity is, one particular speck is different, which happens to then lie on the center of the mask, then we are going to have a very great value, very large value. So it can be used to detect, let's say, isolated points, which could be due to some extraneous effects. There could be some noise. So one black pixel has suddenly become white for some reason, and this will highlight that. And if one can detect it like this, one can also correct it. So that's the whole idea of pre-processing. Okay, let's get an idea about the frequency domain approach. Yes, please. That's right. So what you do is you pad it with some numbers. So it could be you duplicate the first row as a minus or 0th row, or you can fill it with zeros. Anyway, edges are not where you're going to do much of the processing. You will do the processing, but you are not expecting the features to be there at the very edge. If it is the case, then you will not detect it very well. No. The television is not doing this kind of processing. At least the older television did not do any such processing. It is, showed the signal directly. It's only when you're trying to image process and try to enhance something or remove noise automatically, then you have these things which will take place. Okay, so we are now going to appreciate what frequency domain, okay, methods or approach is. Okay, frequency domain approach basically uses Fourier transformations. Okay, as you know that if you given some time domain signal, okay, this is say some f of t as a function of t, it can be represented as a equivalent or alternate way of representing some kind of frequency. Okay, so this is now what is called f of j omega versus omega, where omega has the units of frequency, which is 1 over time, and this is some kind of amplitude and phase of, this is a complex quantity, so it will have a magnitude and a phase in general. So depending on the shape of this, you will get different frequency content or spectra. So this is also called spectra. Now it represents the same amount of information. So now we can do some processing which is in this domain, in the frequency domain rather than in the time domain. Only thing is now we have a image which has got a series of discrete numbers in each of these cells which is representing the intensity. So instead of looking at the time, we are going to look at space. How does it in the space, how is it varying? Instead of time changes, we are looking at changes with respect to increase in one of the variables like x or y, right? So and it is also discrete, so we have to define a discrete Fourier transform. Okay, this is also called DFT. Now DFT, so I can define a function which is a function of frequency u as 1 over n times summation of x going from 0 to n minus 1 f of x. I am now defining a one dimensional first times exponential with imaginary value. So j is square root of minus 1 times u of x, u times x divided by n. Okay, so you look at this. This is what is known as discrete Fourier transform of a function of x, right? And when the transform is applied on this particular function, you get a function, new function, which is a function of frequency. So basically this is what we've done. We started out with, now in place of x, t we have x, and this is f of x, and now equivalent of that we are finding the frequency domain representation in terms of a spectra, which will be, here we have u instead of w, and this is a f of u. Okay. Similarly, we can do the inverse function or inverse transformation, which can be written as u going from 0 to n minus 1 capital Fu, which is the spectral representation, e to the power negative of what we have put here. So that is going to be 2 pi j u x divided by n. Okay. So what I have is basically, if I have a one dimensional image, so one dimensional image is basically pixels arranged in a one dimensional array. each having some number f0, f1, f2, etc., fn minus 1. When I apply this transformation, then I will get a new set of numbers. Now this is going to have f of 0, f of 1, like that up to f of n minus 1, where now these arguments here are representing some kind of frequency variation, right. So I think the best thing to do is to look at an example, and so let us look at an example of some kind of variation in intensity, and I have some value here, some value here, some value here, and some value here. So let me say this is my x0, x1, x2, x3, which may be some intensity values. Let's say this is 0.5, this is 0.75, this is 1, this is 1.25, whatever intensities, right. And I have to know what these values are. So let's say this is some 2, this is 3, this is 4. Simplifying, taking case where we have integral values. Okay. So now what I have is basically I have, just to write it more clearly, x versus f of x. Value of x is 0.5. Then I have intensity is 2, 0.75, intensity is 3, 1, intensity is 4, 1.25, intensity is 4. It is a very small image, so that we can work it out. So if I want to find out my first zeroth frequency magnitude, then I find that this will be 1 over n. If you look at the formula, summation going from n is equal to 0 or x is equal to 0 to 3, okay, f of x e to the power, what do I have for u? U is equal to 0, right. So exponential has 2 pi j minus 2 pi j x times u divided by n, so this becomes all 0 for all the terms, and therefore I get 1 by 4 f0 plus f1 plus f2 plus f3. Okay, that is coming out to be 3.25. Now we take u is equal to 1, then we will get f of 1, and that is 1 by 4 summation 0 to 3 fx e to the power 9. Now I have minus 2 pi j, okay, times 1, which is u, times x divided by n, where x is varying from 0 to 3. So here what I get is 1 by 4 times f of 0. Now when I take f of 0, this term will, exponent will become 0, so we get 1. So this is all we have. Then we have f of 1 times now something which is not 0, and that is e to the power minus pi by 2 times j. Okay. Likewise, next term is going to be, so I am continuing here, f2 times e to the power minus j pi plus f3 times e to the power minus 3 by 2 pi j. Okay. So if I substitute the values, what I get is 1 by 4, 2, which is the first, that f0 is 2, plus 3 times this quantity, which happens to be nothing but minus j, right, e to the power minus j. How would you know that? Well, you should quickly see that this is my real axis and this is imaginary axis. and what we are talking about is e to the power minus pi, sorry, is pi by 2. Yeah, so let me correct that. Oh, that is pi. Here we are talking about this term. Okay, so it's minus pi by 2. So minus pi by 2 is here, which is nothing but minus j, right? So that is there, plus 4 times, now e to the power minus j pi is nothing but 1 or minus 1. So minus 1 plus 4 times, okay, 3 pi by 2 minus is coming up to here, so that is positive j. So that is times j. So this gives me 1 over 4. This is minus 4, this is 2, so this I have minus 2, and this is minus 3j, this is plus 4j, so I have j. So this is the quantity that I get. Okay. Likewise, without actually laboring over it, let us say that we find f2, which turns out to be minus 1 over 4, and f3 turns out to be, calculates out to be minus 1 over 4 times 2 plus j. Okay. So now I have determined all the coefficients of, or all the values of the spectrum, which is represented by capital F0, capital F1, capital F2, and capital F3. Okay. So I can plot that. Now this is my f of u versus u is equal to 0, 1, 2, 3. I have, but I will have to plot 2 items. So what is usually done is you look at the magnitude of f of u. So we are talking about this quantity, and so for f0 this is nothing but 3.25. okay, that's the only real value was there. F of 1 is going to be now, because there are real and imaginary terms, so minus 2 squared plus 1 squared square root. Okay, so that is square root of 5, that is the magnitude. By 4 is there, yes. And likewise I have f2, which is nothing but minus 1 by 4, and the magnitude is going to be plus, okay, because we are taking the absolute value, and f3 is going to have a magnitude of same again, square root of 5 over 4. So if I plot it here, I will have a point here, then I have a point which is slightly more than 1, so somewhere down here, then quarter, and then we have same value again. So this is the spectral representation of that particular image. Okay. Of course, one can go from this back to the original set of intensities by using the inverse discrete Fourier transform. Okay. Now this can be generalized for a 2-dimensional case. So we have 2D discrete Fourier transform. Okay, and in this case, basically, let me just write it down. We will not do any example because that will take too much time. Now we have 2 frequency variables u and v, that is equal to 1 over n summation x going from 0 to n minus 1, summation y going from 0 to n minus 1, f of xy, which is the intensity at that particular location, e to the power minus 2 pi j ux plus vy divided by n, and the inverse will be to give your intensity back from the Fourier transform values, u going from 0 to n minus 1. Actually, you can define it for not n by n image, but it could be some n by m or rectangular image instead of a square image. That is also possible, but let us not worry too much about it. Concept wise we are able to get this, and this is going to be u v, now a positive exponent 2 pi j ux plus vy divided by n. Okay. So here we are talking about now a two dimensional image of intensities. So we have some values of intensities at each of these cells, and this transform will take me. So if this is my y and this is my x, the way I normally keep, then I will get a set of intensities here, a set of Fourier magnitudes, let us say, which will represent the strength of the Fourier term, and I can represent that as an intensity and I can plot it. So this can also be shown, the transform. When I do the transform, my original image will now look like a totally different image of patterns. Okay, and if you are used to seeing it, you will be able to say yes, this feature belongs to that. Key point here is that each of the value that I determine here for any of the cells depends on all the values of the original image, right? This cannot be computed from this alone. It depends on each of the intensity value of the entire image in different weightages, which depends on the exponent that we have, which determines this value, right? And similarly, the other way around also, you can say that if you want to transform back and find out what the intensity here should be, it will depend on all the values in all the cells here. So it is a different type of approach. It is quite useful for doing some frequency domain filtering, high pass filtering which increases sharpness, or low pass filtering which smooths the image. That kind of thing can be done in the frequency domain. Okay, now let us concentrate on our spatial domain approach or operations. Okay, so here we are going to look at one first thing. We are going to look at smoothing. Okay, smoothing is basically used for removal of noise or reduce the effect of random noise. Okay, noise always is present. You have, because of either reflections, or you can have some electronic noise creeping in, the image is going to have some variation in intensity which could be of random type. Now there are different approaches available here, different masks can be used. So let us look at first one, which we call neighborhood average. Averaging. Okay, the idea is that you take a template and we want to find out the average intensity in this neighborhood, and say okay, that should be the new intensity for the central pixel. So if I take 3 by 3 template, then the weights I should give is what? I should give 1 by 9 in each of these cells. Okay, so automatically when I place this mask on different parts of the image, then each of the intensities will get multiplied by 1 by 9, and then we will sum it all together. So it will give me the average intensity, and then that will become the new intensity at the center pixel. Okay, so this is what is the effect, what is the other effect. So what we are doing is, supposing there is some random noise present, we will hope to cancel that by averaging it over a region. Region doesn't have to be 3 by 3, it can be it can be 5 by 5, 7 by 7, 11 by 11, whatever, depends on how smooth you want the processed image to become. Now the disadvantage of that is that you are losing some information. What is going to happen is the sharp edges are going to get dull, especially if my mask is very large, then I will have a very fuzzy kind of boundaries, because as I approach the boundary, the effect of the boundary is felt and that starts showing up in the processed image. So this, the disadvantage is that you get basically a boundaries are softer or fuzzier. Okay. So you will lose information. Supposing you had some text written on it or some small mark which was significant, then it will get lost. So that is, so normally you would not do averaging for more than 5 by 5 mask. It also takes more processing if you have a bigger mask. A better smoothing sometimes is what is called median average. Okay. In this case particularly, we cannot show this as a mask. The idea basically is that if you have a part of the image, supposing I'm applying this to again 3 by 3 and I have some intensities in each of these cells, say I have some image like some 10 here, 12 here, 11 here, I am just making one up, 13 here, 25 here, 2, 10 and say 11. This is one part of the image where I am going to apply both the masks. If I apply the first mask, so in this case neighborhood averaging yields sum of all this, which can be what, 22, 33, 42, 45, 55, 60, 80, 82, 92, 103 divided by 9. So we have 11, roughly about 11 is the average that I am getting here. Okay. But notice that it did get influenced by this particular one. So if this was not 25 but 100 for some reason because there was some noise, then this value will get also changed quite a bit. It will increase by a factor of or by about 10, right. Now if I use median averaging, then what I do is I arrange these intensities in the increasing order. So I have 2 followed by next intensity is 9, next intensity is 10, I have another 10, then I have 11, I have another 11, then I have 12, I have 13 and I have 25. So in median averaging what I do is I look at the then middle value after I have arranged it in a sequence. So it is the 5th one out of 9, and so this is again turns out to be 11 here, right. But you will appreciate that it does not depend on what this value is or what this value is, right. So it gives you immunity from outliners. If some value was very different, then your average does not depend on that. So it is in many cases turns out to be superior. Okay, it requires a little different type of processing and cannot be simply be defined as a mask. Okay. One approach is what is, so we are looking at noise reduction now, smoothing process, something called image averaging. Okay. Here what we are talking about is that we have a one image here with all the intensities, then I have the same image, I have another image of the same scene, I have another image of the same scene, I am just putting them one behind the other. So if I take all the corresponding pixels and find the average of the intensities, then this is called image averaging. So this is intensity averaging across different, well, it is supposed to be the same image, but many images is better than different images. Many images of the same scene, right. This way it is obvious that whatever average random noise is there, if I take many of these images, then I will be able to reduce the noise. I will be able to get lesser variation in, basically the variation which is there because of the randomness is going to be reduced. Of course, it is a time consuming process. You have to have several images to be able to extract out the information, and also yeah, it basically is not that useful, because if you want to do anything in real time, then you do not have information available right away. You have to accumulate several images, and the fact that the images have to be registered, you should not have had any motion of any object in the image. Okay, so the advantage, as I said, is that you get better reduction of noise. Okay, but requires good registration of images. Okay, also time consuming. Okay, final thing I would like to talk about in averaging or smoothing is dealing with binary images. Binary image smoothing. Okay, in binary images, the main difference is that each of the pixels is either 0 or 1. So you can have whatever intensities are only limited to two values, which is 0 and 1. So the processing also becomes correspondingly simpler, because we can process binary images using some kind of Boolean expressions. Okay, Boolean expressions are essentially logic expressions. Okay, so let me now, instead of writing x minus 1, y minus 1, etc., etc., what I am going to do is I am going to, in this particular template, let me label them as A, B, C, D, E, F, G, H, and this center one I am calling P, which is the pixel of which is being processed. Okay, so supposing I have some expression B1 which says P or B and G and D or E, or D and E and B or G, right. You would be familiar that I am calling OR operation of the Boolean as plus sign and dot as, or multiplication as, AND operation. So what does this mean? This means that if I am looking at pixel P, so either pixel P is 1 or B, which is this one, G, which is this one, and one of these two, right. If this is a 1, this is a 1, this is a 1, then even if P was not 1 to begin with, I should put 1 here, right, because that is what this expression is saying. Either P itself is 1, if it is 1, then there is nothing else really matters, because OR it cannot make it 0, right. So it is true, when P is true, that means it is 1, then that is okay. If it is not 1, if it is 0, then it can become a 1 if either these 3 were 1s or these 3 were 1s, or alternately from the second term here, these 3 were 1s or these 3 were 1s. So basically we are saying that if there is a missing pixel, okay, which is part of some object, because there are at least 3 pixels here which are all 1s, so there is, it is not all noise. So therefore this could be made 1. So this is basically going to replace for us fill 1 pixel hole. Okay. Similarly, I can define another expression P and A or B or D and E or G or H or B or C or E and D or F or G. Okay. So here what I am saying is that if P was 0 to begin with, then it will remain 0. If P was 1 to begin with, then depending on A, B or D. So I am looking at this now, this region, if one of these at least was high or true and one of these which is in the opposite side was high, then this should be made a 1. Otherwise it becomes like, it's maybe there was an oblique line passing through here, and so I have these pixels, some of these pixels are 1, some of these pixels are 1, but this is 0, which is possibly because of noise, right? So I am going to fill this up. So it will fill a small notch, one pixel notch. Likewise, I can have another expression, say P or D and F and G and A or B or C or E or H, not of the whole thing. Okay. Now what is this doing? See, if pixel P was 1, then it is okay, it remains 1. If it was not 1, it can become 1 provided 1 out of D, F or G. So basically 1 out of, sorry, all of these, not 1 out of, but all of these were 1, okay, and these were not 1. None of these were 1 and all 3 of these were 1. So what is the operation? You can characterize this by saying that it's going to fill missing corners. And this we have done for the upper right corner. Similar expression I can write for lower left corner or lower right corner or upper left corner, okay, by considering different set of pixels here. So you get the idea that if you have a binary expression, of course the idea is that the processing is very fast here. We are only doing binary operations which are very much natural to the computers, and also we are dealing with pixels which are, so processing can be very fast. Okay. Of course amount of information is less here, but processing can be very fast. We can do some amount of filling of notches, missing pixels, corners, and in general enhance the or make your processed image better than the original image. Now what is better, what is not better, oftentimes will depend on the situation. These are not universal formulas which will be useful everywhere. So it depends on what is the kind of problem the image is having. You will have to design your filters which will take care of that particular problem, and it may create some other problems. So it is a question of a lot of experiences there which you have to utilize to come out with the right filter for the image. So we will stop here.